Hello, everybody. This is going to be a two-part lesson. We'll see how far we can get in this first segment. So we're going to review power series, most likely just some terminology and some things that you've studied already, but it might help to kind of review that. And then we'll talk about how to actually use a power series to find a solution for a differential equation. And the point is, not every single differential equation that you're going to see has an explicit solution that you can just find. So oftentimes what we can do is find a solution in the form of an infinite series. Okay, and so here's some basic info / terminology that you've probably seen, but again, it doesn't hurt to review it. So first, here's the review for a power series definition. Okay, so a power series looks something like this. You have the sum from n equals 0 to infinity. Then you got c sub n, which represents your coefficients, and then times the quantity x minus a to the n power. Okay, and if we write this out, plug in 0, plug in 1, plug in 2, and so on, you get what looks like c0 plus c1 times x minus a to the first plus c2 times x minus a to the second, and so on. Okay, and we call this a power series centered at a. Okay? Now, we also need to talk about convergence. And basically, if the limit as capital N approaches infinity of the sum little n go from 0 to big N of c sub n x minus a to the n. So if this limit exists, okay, at a specified x value, then it converges. If the limit does not exist, and the series diverges. Okay. Now, what we're going to probably focus some of our time in is going to be finding intervals and radii of convergence. So let's highlight that. And we'll talk about how to find these momentarily. An interval of convergence is the set of all numbers for which the series converges. And now the radius of convergence what you need to know here is that every power series, I'll just abbreviate that PS, has a radius of convergence. If the radius is greater than 0, then the power series converges. For the absolute value of x minus a less than r. if it only converges at where it's centered at x equals a, then obviously the radius of convergence is going to be 0. Okay? And what you also need to remember is that even though we might have a radius of convergence, the power series may or may not converge at the endpoints. And again, those are a minus r and a plus r. Okay, so once you've established what the radius of convergence is going to be, you do have to check at each endpoint to find the final interval of convergence. And we'll do an example of that again in a little bit. All right. Again, I'm not highlighting everything that you learned about power series, just some things that'll be helpful moving forward. All right, so then we also have absolute convergence. And what that means is that for any x in the interval from a minus r to a plus r, that the series will the absolute series converges. In other words, the absolute value of c sub n times the absolute value of x minus a to the n converges. Okay. Now, finding the interval of convergence. So we'll outline so oftentimes what we're going to do is just the ratio test. We're going to keep things simple. Okay, so let's review that. The ratio test was just the limit as starts with the limit as n approaches infinity of the absolute value of c sub n plus 1 over c sub n times the absolute value of x minus a equal to L. So we start with this equation, right? So we're taking the ratio of coefficients, and what we know is that the series converges absolutely for x such that this L value is less than 1. Okay? So to find what the radius of convergence is going to be, you set L equal to 1. So imagine that this equals 1, right? And then the ratio of c sub n plus 1 over c sub n, okay, if we move it to the other side, okay, we're going to get r is going to be the limit as n approaches infinity of c sub n over c sub n plus 1, the absolute value of that. Okay, so this is what we're going to use to find the radius of convergence. All right. A couple other terminology / definition bits. We'll skip that. Zero series, I mean, if it's zero for all the coefficients, that's not too hard. But this stuff will come up again later, so let's talk about it now. Analytic at a point. If f can be represented by a power series in x minus a with a radius greater than 0, it is analytic at point A. Okay. And finally, arithmetic of power series. I guess all that needs to be said here is that we can add, multiply, subtract, divide power series just like polynomials. Okay, so I know that was quick and it was just me kind of saying all these things, right? But this is stuff that I think was covered in Calc 2 or BC Calc when you guys did series, and we're going to focus just on bits and pieces of this. But again, the highlight for us is going to be finding an interval of convergence, actually doing some arithmetic here, like adding and subtracting or multiplying and dividing some series to create a new series, and then that will come in handy when we start finding a power series solution. So let's go ahead and run through an example of finding an interval of convergence. And let's say the series is from n equals 1 to infinity, and we've got x minus 3 to the n over 2 to the n times n. All right, so first we're going to find the radius using that equation that we reviewed a minute or two ago. The limit as n approaches infinity of c sub n over c sub n plus 1. Okay, and so if I actually look at the c sub n, we're talking about 1 over, right? 1 over 2 to the n times n. Those are our coefficients equations for n. So c sub n would just be 1 over 2 to the n times n. C sub n plus 1 would be same thing, just replace n with n plus 1. Oh, and I'm sorry, forgot to write down, we're still taking the limit as n approaches infinity of this, okay? And so I'm just going to simplify and see where that takes us. So I can certainly rewrite this complex fraction, put the 2 to the n plus 1 times n plus 1 in the numerator, and then we still got 2 to the n times n. And so that we can simplify. 2 to the n plus 1 over 2 to the n, you subtract the exponents, the n's cancel out, you're just going to get 2. And then you got n plus 1 over n. Okay, and this is not a hard limit, right? This portion has a limit equal to 1 as n goes to infinity. And so the limit value is going to be 2. Okay, so then that means to find the interval of convergence, We take x minus 3, the absolute value of that, we set it less than 2. So this is for the interval. You take the radius, you take the power series form, not just remove the coefficients basically, and the exponent. X minus 3 less than 2. You solve that. Let's see, so that's the same as negative 2 less than x minus 3 less than 2. Add 3 to everything. We get 1 is less than x, which is less than 5. Okay. And final piece, test the endpoints. So far we've established that the interval of convergence is the open interval from 1 to 5. It's possible that we might have convergence at 1 and or 5, or neither, but we're going to test the endpoints. So at x equals 1, here's what we're talking about. So at x equals 1, we take n equals 1 to infinity, the sum of that, and now I'm just going to replace x with 1, so we're going to get negative 2 to the n over 2 to the n times n. And so we got a negative inside the exponent, or a negative is part of the base rather. So I'm thinking alternating series here. So let's see if we can write it. So we can do negative 2 to the n is the same as negative 1 to the n times 2 to the n over 2 to the n times n. Two to the n's cancel out. So now we're left with the sum from n equals 1 to infinity of negative 1 to the n over n. Okay, and this converges by the alternating series test. Okay, alternating series test. We know it's alternating because of the negative 1 to the n. So if you write out all the terms, starting with 1, you'll get negative 1, and then plug in 2, you get plus 1 over 2. And so we get that alternating pattern. And as long as that alternating series is decreasing term by term, if you're just looking at the absolute value of it, so we're going 1, 1/2, 1/3, and so on, that's how we know that the alternating series will converge. Okay. Now, what's going on at x equals 5? At x equals 5, plug in 5, we're going to get 2 to the n over 2 to the n times n. Cancel out the 2 to the n's. You're left with the series of 1 over n from 1 to infinity. And that we know is a divergent series. So what we've established is that at 1, we do have convergence. So the interval of convergence is going to be from 1 to 5, but the 1 will get included, the 5 will not. Okay? Because at 1 we had convergence, at 5 we did not. So that's kind of how that works there. All right, I think we have time for at least a little bit of arithmetic, at least one example. Let's say I want to find the first 4 terms of e to the x times cosine x. So if we write out the series for e to the x, we know that that's 1 plus x squared over 2 factorial plus plus x cubed over 3 factorial, and so on. And cosine of x starts at 1, and then we do every other term up here basically and alternate. So minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. So what does e to the x cosine x look like? Well, let's just stick these together. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, and so on. We're going to multiply that with 1 minus x squared over 2 factorial. I'm just writing down the series for cosine. A couple more terms. Hey.
Sorry, I've been stalking you via GChat, which I realized.
I'm kind of recording a video for class. But can you come back in like 5-10 minutes? Is that possible?
No, I have study help. Can you just message me?
What room are you in?
247.
I'll come find you. All right.
243.
243. Got it. Sorry about that, guys. Okay, continuing. So we're doing e to the x cosine x, and we're going to multiply the e to the x expansion with the cosine x expansion. But again, all we care about are the first 4 terms, right? And so let's just kind of look at a few of these. So I'm going to start with just, okay, we got our constant, obviously, because you got 1 times 1. We have our linear term, which is going to come from x times 1. And so I'm going constant, linear, quadratic, cubic, and I'm just going to write down the coefficients as I go. So I'm not actually going to like multiply it all out. I'm just going to selectively multiply what I need to create my constants, my linears, my quadratics, and my cubics. Okay? So I know I have a 1, I know I have an x. Let's take a look at my x squared stuff. So where would I get x squared from? Well, I'm going to get x squared when I multiply 1 with negative x squared over 2 factorial. So negative 1 over 2 factorial. And I'm also going to get x squared when I multiply x squared over 2 factorial with this one. And so the coefficient there would just be 1 over 2 factorial. Okay, so let's look at the cubics now. So for cubics, I'm going to have this x times the x squared. That'll be my x cubed term. So that'll be minus 1 over 2 factorial. And I'll get a cubic when I take x cubed times 1. That's plus 1 over 3 factorial. And I'm going to go one more because even though technically these are the first 4 terms, the x squared term goes out, cancels out entirely, right? Because this is just going to be 0 for the coefficient. So I have 1, 2, I have the third term right here. I'm just going to figure out the next one and hope that that's good. So where do I get x to the 4th from? Well, I'm going to get x to the 4th, let's see, from right here, x squared times x squared. So that'll be 1 over 2 factorial times negative 1 over 2 factorial. I will also get x to the 4 from 1 and x to the 4 right there. So that's going to be plus 1 over 4 factorial. And one more here, x to the 4 with this one. So that's another 1 over 4 factorial. And I think that's it. So those are the coefficients for x to the 4. And then so if we simplify everything, I get 1 plus x. This is really negative 1/2. 3 factorial is really 6. And now, what's this going to be? So half times negative 1/2 is negative 1/4. And then we have plus 1 over 4 factorial, that's 1 over 24, 2 of those, times x to the 4. And so if you simplify everything, negative 3/6 and 1/6, that's going to be minus 1/3. So minus x cubed over 3. And then here, that's 2/24, which is the same as 1/12. So negative 3/12 plus 2/12, that's minus 1/6. So minus x to the 4 over 6, plus etc. So all we cared about was the first 4 terms, and here they are. All right, so that's a little bit of an intro, well, more of a review of power series, and a little bit of an introduction of how to multiply some power series together to create a new power series expansion. The next portion of the notes we will pick up, we'll do a division example, and then actually how to add 2 power series together, what that entails, and then we'll be ready to apply what we've been talking about in solving a differential equation. All right, see you guys later.